Welcome back. I've just realised that I've got some green in my t-shirt, and it's always funny when you make the mistake of wearing green clothes with green screens because you find you can sort of see through your own body. The background is a little temple in suburb of Tokyo called Ningyōchō, and one of the nice things about living in Tokyo is that you realize there's so many temples all over the place that you don't have to go to the really big crowded ones that are full of tourists. You can go and find ones that are sort of almost equivalently good and nowhere near as busy. Anyway, this one at the background is particularly nice, and it's just up the road from Ningyōchō station. So, should I take that again? I will take that again. Going to have a lot of editing work when I come through in here. Kappa. Welcome back. I've just realized that my t-shirt has a little bit of green in it, and so this is always the amusing thing when you're working with green screens and you accidentally wear clothes that have got green. You find out that some parts of your body become see-through. On the background, one of the nice things about living in Tokyo is that there's temples all over the place, and many of them are really, really good. And so that means that you can kind of skip some of the really heavily touristed, crowded temples that are in all the Lonely Planet guides and go and find the ones that are almost equivalently good, but much less crowded. And so this is a nice little temple just up the road from Ningyōchō station. Basically translates as Doll Town. And it's, yeah, particularly nice and very much not crowded. And well worth the look if you're floating around in Tokyo and looking to get away from all the usual tourist traps. So we spent the last lecture basically getting equations for forced harmonic oscillators and resonance situations. And what we did was get an expression for the amplitude, an expression for the phase, and then work out where the maximum amplitude is going to happen. And we worked out where, but we didn't work out what that maximum amplitude is. So in this half, I'm going to come back and look at that. I also want to have a look at some plots of amplitude and phase. And I want to look at some other things connected to resonance peaks that are useful in terms of applications and quantifying resonance in physical systems. So the place we have to start here is we have to look at two limits, the weak damping and the strong damping limit. And we can now see where these emerge because of the equation that we just got above in the last half of the lecture. Spell correctly. Strong damping. So the weak damping limit, what we normally assume here is that omega naught is much greater than gamma. And if you consider this equation we got right at the end of the first half of the lecture, just up here, if you take 2 gamma squared and you make it really small, then this term under the square root basically becomes omega naught squared. And what that means is the resonance frequency is basically equal to omega naught. Okay, so this is sort of the limit where omega r is equal to omega naught. Okay, this weak damping limit. And what you'll notice here is that basically your resonance frequency is determined entirely by the spring constant and the mass. The strong damping limit we define as gamma greater than or equal to omega naught on square root of 2. And at the moment that might seem like a really arbitrary thing to choose, but if you consider this term up the top here, if you take gamma squared, you will get omega naught squared over 2. 2 gamma squared will be omega naught squared. The term under the square root is omega naught squared minus omega naught squared is 0. And so this is basically the point where your resonance frequency becomes exactly 0. Okay? And so often in physics we're kind of interested mostly for understanding how resonance works in sort of this range here from sort of very weak or no almost no damping, right through to up against the strong damping limit, because that's where we can understand the behavior of resonance. And then often this strong damping limit, so this region up here, is more of use if you want to get rid of resonant effects. Okay. All right, so with that out of the way, because we need to understand that to look at the graphs, I'm going to show you graphs of amplitude and phase for this system. And before I do that, I'm going to point to one of the interesting things that sometimes happens, particularly when you're teaching a course for the first time, which is you're always sort of following other people in terms of how to design your course. And one of the bad habits you can get into is basically assuming that somebody else has drawn something that's correct, and then when you sit down to explain it, you realize actually it's not correct. So this graph, what we're plotting here is the amplitude A versus omega, and you can plot the equation for that as a function of different gammas. And you can do this yourself tonight in a mathematical program. Just take it out and do these plots, and you'll see that the blue lines here are actually quite correct, or reasonably correct, okay? As best as you can draw them. So let's consider first the weak damping limit. In this weak damping limit, what you get is a peak in the amplitude, and that peak in the amplitude happens either at or very close to omega naught, okay? As you increase the damping, what will happen is that peak will shift to lower frequencies from omega naught. And the reason for that is if you look at this point up in here again, gamma squared is always positive, omega naught minus a positive is always less than omega naught, and so omega at the front is always going to be less than omega naught, okay? So this is two things that you know in resonance systems. If you increase the damping, you're always going to drive the resonance frequency to lower frequency, and the highest frequency where you can expect a resonance in the system will be square root k over m, okay? And this is actually useful if you're trying to design systems to avoid resonance. You can work out what the maximum frequency that will excite a resonance is and design your system so that, you know, all of your driving forces that would generate resonances are at frequencies higher than the frequency omega naught, which is your maximum resonant frequency for the system, okay? So sure enough, as we increase the damping, this peak both moves towards lower omega, and it also decreases in height. We get a loss here. And so what's really going on is you get a loss in the height of the peak, you get a broadening in the peak as well, okay? The thing that's wrong in this graph that I suddenly realize is this dashed line running down here, okay? This dashed line actually should come down through these peaks, which is correct, but then it should skip off down here and end up down in here somewhere, okay? So as you increase your damping, what happens is this peak basically races off towards 0 very, very quickly. And your peak broadens right out. And then you reach the point where the resonance frequency has become 0 and you now no longer have a peak in here, okay? So you can see you've gone from a function with a peak to a monotonic dependence in omega naught, and this is now your strong damping limit down in here, okay? For the students taking my course, I'll update this graph in the notes and reissue a new set of notes. For the people watching the recording, you're just going to have to take note of the fact that this dotted line should come in here rather than follow the path that's on the diagram. One of the joys of teaching a course for the first time is sometimes realizing that you get a better understanding of a subject by explaining it. It's one of the cruelties of the academic system in many ways is that sometimes the lecturer learns more than the student because you basically have to learn by teaching, and you learn more by teaching sometimes than by being taught. Okay, so that's that graph. Let's have a quick look at the phase. So we've got two plots here. First, we can look at just the expression tan phi versus omega, okay? And to foreshadow this graph, I'm going to scroll back up in the notes for a second. What we're interested in here is this term just here, okay? If you have a look at that term, the numerator looks fine, the denominator is omega naught squared minus omega squared, and you know that that thing is going to go to 0 at some point. When omega is equal to omega naught, you can have omega naught squared minus omega naught squared. That's going to go to 0, and so your graph is going to blow up. Okay, and so sure enough, your tan phi here will be well behaved in the high and low frequency limits, and then as you approach omega naught from either side in this particular case, you'll end up with that function blowing up on you. The next step in this is to basically take the inverse tan of that equation we had and basically plot phi. Okay, and again, you can do this for yourself with a graphing program and you'll get much better graphs than I'm drawing on the page. And what you get here is your phi will go from a phase of almost 0 in the low frequency limit to a phase of almost pi in the high frequency limit, and it will cross very sharply through your pi on 2 value at your resonant frequency omega naught. And then as you tune the damping in this system, basically what happens is you wash out that very sharp graph into just something that sort of passes through the middle. Okay, I'll let you play with phase for yourself. It is kind of interesting to sit down and do it, but usually when we're dealing with resonance systems, we're more interested in the amplitude than we are in the phase. Okay, so with a limited amount of time to deal with things in this course, I'll let you play with a phase and I'll go back to focusing on the amplitude. So the thing we want to do here is to basically get the maximum amplitude for our system, because we know where that maximum is, we don't know what that maximum amplitude is. Whoops, change color. And we have this equation here, F naught on M on our sort of resonance denominator, D of omega. And I'm not going to write that out yet because I'm going to be writing that out below. But we know that our peak Amax happens at our resonance frequency, which is omega naught squared minus 2 gamma squared to the half. Okay? All right, so it's pretty obvious in here what we're going to have to do is attack this denominator and clean it up a little bit, okay? And the best way to do it, since we're interested in the amplitude at a specific frequency, which is the resonance frequency, is to just substitute that into that denominator and use that to simplify, okay? So let's do that. We'll attack the denominator. And whether it's writing out problems or writing out exams or whatever, sometimes it's actually the smart option is, rather than to write the whole equation again and again and again, is just to mention that you're going to pick up one term and deal with that term, okay? All right, so what we've got here is, and we need to be a little bit careful, this is going to be omega naught squared minus, the term that follows that would be omega squared, right? So we're going to have a square in here, and then this is going to be omega naught squared minus 2 gamma squared to the half. So let's just bring this square in. And then there's another squared on the end of this for that term out the front, right? So if you, if we scroll back up here and look for our denominator, just here, it's omega naught squared minus omega squared squared. Okay, so that's where this second square term is coming, just in here. Okay, and then we add on here 4 gamma squared omega naught squared minus 2 gamma squared to the half squared to the half. Okay, and so if we just scroll back up to where that d of omega was again, just for a quick look, where is it hiding? Just here. This term on the end here is basically 4 gamma squared omega squared, right? If we have a look down here, 4 gamma squared omega squared on the end. Okay, so the nice thing about cleaning this up is that we kind of get a little bit of a attrition of our square roots and our squares in here. So this square will take care of that square root, and this square will take care of this square root. And then all that's left here that we have to worry about is that square and that square root on the end, okay? All right, so let's do this. What we've got is omega naught squared minus, those two take care of each other, so this will be omega naught squared plus 2 gamma squared. And then we'll have a square in here, plus 4 gamma squared. We can expand this out straight up, so that term, and then these two terms on the end will become minus 8 gamma to the power of 4, and we keep our half on the end here, okay? All right, so next step in here is that this term kills that term, which is kind of convenient, and so what we're left with here is 4 gamma to the power of 4 plus 4 gamma squared omega naught squared minus 8 gamma to the power of 4 to the half. So you can see this thing's collapsing quite nicely on us now. The first and the last terms will clean up a little bit here as well. So what we've got is 4 gamma squared omega naught squared minus 4 gamma to the power of 4 to the half. And then when we take this all through, we can factorize out the 4 and a gamma squared out of this, right? So this would then be 4 gamma squared omega naught squared minus gamma squared to the half. And when we do this, this will end up being 2 gamma out the front, square root omega naught squared minus gamma squared. Okay, so that denominator has cleaned itself up quite nicely and becomes something that's quite useful to us. And so we can write down here our maximum amplitude is going to be F naught on M divided by 2 gamma square root omega naught squared minus gamma squared. And so if you come back to your graph of amplitude here, you should be able to make a prediction about what the peak amplitude is, and when you graph it, you should find that you get that peak, okay? Now, there's a way we often write this, which is a little bit simpler, which is just to go F naught on C omega D, okay? And this relies on the fact that gamma is C on 2M. Our omega D is a term we're going to define here that we call omega naught squared minus gamma squared. And the interesting thing to note, and I'll let you prove this for yourself, is that omega R is equal to omega D squared minus gamma squared to the half, okay? And so I'm going to leave this as an exercise for you in here, because it's actually just a little bit of algebra to play with. You should be able to get from this expression here to this expression here fairly easily by working your way through those terms, and you should also check that this thing really holds, okay? Just useful little relationships in here. Okay, so we've got this expression for the maximum amplitude, and often we care about the weak damping limit because if you've got a resonance system, you either want to get rid of the resonances, so you go off to the strong damping limit, or you want to make the resonance a feature, so you want to reduce the damping and go to the weak damping limit, okay? So what we can do is take the we can take the limit of small gamma, and if we do that, then what happens is the term up here, which is square root omega naught squared minus gamma squared, is going to do the same thing that we saw earlier up when we were dealing with this equation here, okay? So what's going to happen here is this is going to become like square root of omega naught squared, and this thing is going to become roughly omega naught, okay? And so now we can write a simplified expression for our A max, which is F naught on 2 gamma m omega naught. And this thing basically just becomes F naught on C omega naught, okay? And the main reason to have this is that it's just a simpler expression that doesn't require us to get omega d anymore. We basically just assume that the resonant frequency happens at omega naught, okay? All right, so that's the amplitude of our peak up the top here. Another thing that we're often interested in is the width of that peak, okay? So you notice as you move down through this graph, that peak gets wider and wider and wider, okay? And so we can come up with an expression for that as well. So let's deal here with peak width. Whenever we do peak width, we usually do it in the weak damping limit. Just to keep things nice and simple, okay? And often because if you care about it, you want resonance as a feature and you're trying to keep your damping low, okay? If you need to deal with systems where the damping is not weak and not strong, then this gets a little bit more complicated as an argument. So what we have here is gamma is much smaller than omega naught, and we can go back to our amplitude expression in a minute with two approximations that will simplify that expression. And the nice thing here is that these two approximations are rather common in dealing not just with mechanics but in physical problems in general, okay? So it's worth paying a little bit of attention to these because they turn up again later and later in your physics education. So the first approximation we can take here is we have a term that looks like omega naught squared minus omega squared, okay? And we know that this thing can be factorized as basically omega naught plus omega times omega naught minus omega, right? And then the approximation we take here is that omega is roughly omega naught for gamma, much less than omega naught, right? And the important thing that we're going to do here is we're going to assume that omega is not quite omega naught, but it's close to it, right? And it's the reason why I say that is because this first term up here, what I can do is I can write it as 2 omega naught by putting omega is roughly equal to omega naught into this term, right? But what you'll notice is if I try to do that for the second term, omega naught minus omega, I'm going to get omega naught minus omega naught, which is 0. And my approximation is that this thing's gone, right? Which is not very useful to me. So what I'm going to do is leave this second term alone. And I know it will be small. I just don't want it to become 0. Otherwise the problem evaporates on me. Really common approximation. And you can only use it for omega not equal to 0. So here what we're going to do is stay away from the peak, which is okay. We're interested in the width, so we're going to be operating away from the peak. And we're not going to be very far away from the peak. So this approximation is okay as long as we stay in the range where it's valid to do it, okay? Second one's even simpler. What we're going to do is go gamma omega is roughly equal to gamma omega naught, okay? And now we're going to come back into our amplitude term and we're going to try and use this thing in here, okay? So let's write this out just so we have a place to start. Okay, so we're dealing with an expression that looks like this. And what we're going to do is now use our approximation in here. So this is going to be F naught on M. And, you know, if I wanted to, I could just write off, I'm going to attack the denominator and sort out the denominator and do it that way, okay? Actually, I might do that. It'll save me some writing in here. So I'm going to take this denominator and clean it up, okay? So what I'm going to do is go square bracket. This omega naught squared minus omega squared, I'm going to make now 2 omega naught minus omega. And of course, I have to square that, plus 4. And then my gamma omega is now going to become gamma omega naught, so it's going to become gamma squared omega naught squared, and I'm going to have a half on the end here, okay? All right, so I've got to square this term in here up the front. So this is now going to be, actually let me move left a little bit just so I've got some more room. So this is going to be 4 omega naught squared omega naught minus omega naught minus omega, plus 4 gamma squared omega naught squared, like so, right? I can multiply out these terms in the middle, so let's keep this. This is now going to be omega naught squared minus 2 omega naught plus omega squared, like so. I can now expand this whole thing out. So what this will give me is 4 omega naught to the power of 4 minus 8 omega naught to the power of 3 plus 4 omega naught squared omega squared plus 4 gamma squared omega naught squared to the half just here. And you'll notice in here that I've got a common factor of 4 omega naught squared all the way through this, right? So what I can do is isolate that common factor. So 4 omega naught squared, I'm going to have this term will give me omega naught squared. This term will give me minus 2 omega naught. This term here will give me plus omega squared, and then this term here will give me 4. Actually, no, I won't have a 4 there. I'll just have the gamma squared. And so then I can enact this square root on the end. This will give me 2 omega naught. This term here I can factorize again. So this will now be omega naught minus omega squared plus gamma squared on the end here to the power of a half, okay? All right, so now I can rebuild this. A of omega is going to be F naught on M, 2 omega naught minus omega squared plus gamma squared to the half, okay? Okay, so I know that my maximum amplitude is going to be F naught on 2 gamma M omega naught, okay? We got this a little bit further up. And I can rearrange this thing so that it looks like, F naught on M on 2 omega naught. And so you notice what I'm writing here is basically sum of the expression in the line above is equal to A max times gamma, okay? So all I've done here is basically take this little m down here and push it up to the top line, and taken this gamma and pushed it across to the other side, okay? And so now what I can write is an expression that looks like this. A max gamma on square root omega naught minus omega squared plus gamma squared, okay? And this thing here, hanging off the end, it's an interesting curve. My initial gut feeling goes, oh, hang on, this is a Lorentzian. And it's not. So a Lorentzian looks like this. L of x is 1 on pi, a half gamma on x minus x naught squared plus a half gamma squared, right? But one thing you know about this Lorentzian is that it will be a peak like this, and it will be centered at x naught, and it will have some width at half maximum of gamma, right? And although this thing is not a Lorentzian, it's rather similar, right? In the sense that you have a peak, and that peak will be centered at an omega naught, and it will have some width, and that width we can see is going to sort of be tied to gamma, okay? So let's come down here now and just consider A of omega when omega naught minus omega is equal to gamma, okay? And just a quick back comment for a second. If you haven't seen a Lorentzian before, don't worry too much about it. It will be coming back for you if you do higher year physics. Those of you who've already seen it, I'm just drawing a connection. Okay, so if we consider this particular case here, then A of omega will be A max gamma on square root of gamma squared just here plus gamma squared just here, right? And of course this thing is A max gamma on square root of 2 gamma. And then the gammas cancel out here, so this is A max on square root of 2, okay? And so if you take the amplitude squared, it is going to be the half A max squared in this particular case, okay? So what's interesting here is that this condition that we just took, omega naught minus omega is equal to gamma, is equivalent to the case where omega is equal to omega naught plus or minus gamma, okay? And so what we're really saying here is if we have our resonant peak, if we go to omega naught, which is the middle, and we go plus gamma or minus gamma from that, we end up at the point where the square of the amplitude at that position is half the square of the maximum amplitude of the system, okay? And this is a thing that we essentially define as the peak width, 2 gamma. And just to bring up a more focused graph of this, imagine we now focus on this resonance peak in a situation where the damping is very weak, so we get a nice sharp peak, and we ignore, you know, way out in the very low and very high omega regions. If we look in close, we get this nice symmetric peak in here, or nearly symmetric peak in here, peaks at nearly omega naught with an amplitude maximum, and then we end up with 2 gamma being the width at the point where we're 1 over square root 2 of the amplitude, okay? And the reason why this amplitude on root 2 is interesting is because you know for many systems, you learn this in first year, whether it's light or sound, that the energy goes as the square of the amplitude, okay? So this is actually the half energy point for the system, right? So if you have a resonant peak, the width of the peak at half the energy will be 2 times gamma, and so you can control that peak width via the damping term, okay? So you'll notice in here in this weak damping limit, the position of the peak is set by k over m, and the width of the peak is set by a variable that's connected to c over m, okay? Nice way physically of looking at this system. And so the last thing I want to point out here, and it's very, very quick, is that we have a thing in talking about these peaks that we call the sharpness, right? We've got two different measures. We've got height of the peak, which is the amplitude max, and now we've got the width of the peak, which is sort of governed by 2 gamma. And often you care more about the relationship between those two things than what they individually are. And so we can define a parameter for sort of the sharpness of the peak, right? So you can imagine you've got a very tall, very narrow peak. That's a sharp peak. If you've got a very wide, very flat peak, then that's, you know, not very sharp peak. And so we often define sharpness here by a thing that we call a quality factor. And it's always called Q, right? So often you'll hear this called the Q factor or the Q for the resonator. And we define this thing Q as omega D on 2 gamma, okay? So it's basically the omega D we had a little bit further up, which in the really weak damping limit approximates to omega naught. So it's the actual position of the resonance divided by the width to 2 gamma, okay? And so in the limit of small gamma, you know that omega D is roughly equal to omega naught, and so this thing becomes Q is omega naught on 2 gamma, okay? And if you want, you remember that this thing here is square root K over M. This thing here is C over 2M. And so you could write this as a Q in terms of the physical parameters of that system, K, M, and C. I'll let you do that for yourself as an exercise. You can basically work out what the Q factor for a resonator is based on its physical properties. And then if you want to design very high Q, you can tune those parameters to give you very high Q, okay? And so I'll let you play with this for yourself. You can take it as an exercise tonight. How would you design a really high Q mechanical resonator, and how would you design a very low Q mechanical resonator, given that you can tune K, M, and C, okay? All right. We can take one last step here, which is to get the total width at half energy. And so we have delta omega here, which is just 2 gamma, and it will be omega naught on Q, okay? So we now know roughly what the frequency width of this is. It's just the omega naught divided by the Q factor. And the last little bit in here is that we can write this a bit like this: delta omega on omega naught, which is the same thing as delta F on F naught, is roughly equal to 1 over Q. Okay, and so experimentally, if you want to extract out 1 over Q, you need to get those two variables. Okay. All right, that's pretty much all I wanted to cover on resonance, and I just want to finish off by pointing out that you don't just have to have mechanical systems, you know, like masses on springs and wine glasses and stuff, giving you resonances. And so this year is a bit unusual because of coronavirus, but in a normal year, in your mechanics course, you would possibly come across an experiment on electrical circuits, and students always go, oh, hang on, this is circuits, how does this have anything to do with mechanics? Actually, it does. So the experiment is basically to design an RLC circuit. You'll have seen this potentially in your first year courses. You basically take a resistor, an inductor, and a capacitor, you put them in series, you put a time-dependent voltage or current into this system, and what you get is the same behavior that we saw today for our mechanical oscillator, in terms of resonance and damping and so forth, right? And so you can basically take this system in here and write the equivalent of an equation of motion for it. Those of you who are curious can do this as an exercise tonight. Pop back to your first year textbook, try and connect the oscillator equation of motion we had today, mx double dot plus kx plus plus kx dot, mx double dot plus cx dot plus kx equals 0. I'm trying to run too fast. And connect that up to an equation like this one in terms of your inductance, your resistance, and your capacitance in this circuit. And you can solve that in much the same way, and you get much the same physics out. And just to highlight that, in our spring system, your omega naught is square root k over m. And as you work out in your electrostatics lectures, your omega naught for one of these RLC circuits ends up being 1 over LC, okay? And so then you can imagine, you can see earlier on why I wanted to shift from working in C, M, and K to working in omega naught and gamma, because that means I can take the same physics that I've done for my spring-based system and transfer it across to an electrical circuit that has the same behavior. I can transfer it to some other system as well. I've got some common framework, and all I've got to do is work out what omega naught and gamma are in that new mechanical system, okay? And one of the nice things about resonance circuits is that you really do get resonances. And so I'm going to connect this back to one of the sort of first science experiments that you used to get to do as a young child back when I was a young child, which, you know, under the Christmas tree would turn up something like this over on the left, crystal radio kit. And essentially, it's a really good example of a resonance circuit being run at a resonant frequency. So what you do is you tune that circuit to an external oscillation, right? So you have your radio station puts out an electromagnetic wave. That electromagnetic wave is at a particular frequency. You then take your RLC circuit, and usually in here you've got an inductor, which is just a wound coil. You've got a variable capacitor, so it's a set of plates that on an axis, so you can tune the capacitance. And then you'll have some resistance in this circuit, or you might just use parasitics to handle this. And you tune this circuit so that the external electromagnetic excitation is tuned to that circuit. It will drive an oscillation in that circuit very strongly. Then you can rectify that signal and pull that out through earphones, which you can see just down here. And the nice thing about this crystal radio circuit is, and particularly good on Christmas, because the thing that was always horrible was you'd get all these toys and then you didn't have batteries for them, so you couldn't play with them until the next day when you finally worked out what batteries you need and went to the shop and bought the batteries. Those were the days before they sometimes put on the outside what you needed. The nice thing about crystal radio is you don't need a battery. The whole circuit is basically driven off the energy that comes from the excitation. And this is a little bit like the kid on the swing. You no longer have a push. You're basically self-driving the system, and you derive all of the behavior from that excitation driving your resonance. And in this particular case, it even drives the earphone, which you design in such a way that it runs really well on low amounts of power. So I think I'll finish there.
Hello, students. School has begun. The summer is over. I am in command. What was that? For that little outburst, each and every one of you will spend 3 hours in detention today, immediately after school, in the basement. What do you think you're doing? Twisted sister, what kind of a man desecrates a defenseless textbook? I've got a good mind to slap your fat face. You are destroying your life with that garbage. All right, Mr. Sister, I want you to tell me, no, better yet, stand up and tell the class. What do you want to do with your life?
I want to go to UNSW and study physics. And then I want to rock.